Okay, so just taking a look at the remainder of the packet that we did cover last class. So we kind of started in the middle of our skeletal packet last time because I really wanted to highlight the position of the bones, the major features that you have on the bones that you guys can use to identify them in getting ready for the midterm that you guys have on the 12th. So for today, we're actually going to backtrack and go to the beginning of the packet to talk about some of that basic skeleton information. So when we talk about the skeleton, by the time you get to the human adult skeleton, you have 206 total bones. And the development of the bones is an ongoing process. It's not something that at birth you have these fully ossified bones. We do have several of our bones that start out as a cartilage base, so it has the framework and the shape of the bone, but it doesn't have all of the calcium deposits and everything that is going to give it the strength that we typically associate with our bones. So that is very much a process, and I highlighted that in a couple places, excuse me, with like the patella not fully coming into a bone type structure until you're 2 to 6 years old, talking about how the plates of the skull will not fully fuse together until you reach your mid-20s. And so there's lots of places within the skeleton where there is change and a process to go through to get it to be the full bone structure that we typically think of. And even once your bones are fully ossified, you still have bone cells that are dying and have to be replaced. So that's another feature of bones that is kind of hard for some people to grasp onto, that they are dynamic, they are constantly changing. Just like your other soft tissues, as cells die off, they do have to be replaced. So looking at the skeletal information, one of the things that we did talk about last time is the two divisions of the skeleton in the appendicular and the axial skeleton. And of those 206 bones, we have a division where 80 of those bones are going to belong to the axial skeleton. So those bones that are right on the midline of the body, 80 of those bones are found in that portion of the skeleton. The remaining 126 are going to be found in the appendicular skeleton, so the shoulder girdle, the arm, the hip girdle or pelvic girdle, and then the legs themselves, all the way down to the feet. So it's not an even division when we look at where the bones are located between the appendicular and the axial skeleton. I want you guys to find the slide in your packet that talks about the types of bones. And so the bone structure is slightly different depending on the job that the bone has to do. If it is a bone that is going to be used to move the body, it's usually long and narrow. If it is a bone that is going to protect, then it is going to be rounded in its shape or formation. And if it is a bone that is going to allow for range of motion, then they're typically smaller bones. So if you think about your fingers and all of the movements that you guys can do with your fingers, that is because you have multiple small bones that make up your fingers themselves. And because those bones are small, you have all of those different movements that you can carry out with them. So the design of the bone is very, very important to the job that it has to carry out. So when we look at the types of bones, the first one that you have on there identifies long bones. This is going to be a bone that is taller than it is wide, so a long and narrow bone. And these long bones are going to be used in typically your limbs, and they are for moving things. So we have the femur, which is the longest bone that we have. You have the two bones of the lower leg, which would be considered long bones as well. The tibia and the fibula, and then the bones of the arm, humerus, and then your ulna and your radius. All of those are longer than they are wide, and they would fall into that long bone category. And then you have your short bones. Short bones are going to be a little bit closer in their height than their width. Not perfect, but they are going to be much closer than what you would see with your long bones. The short bones would be found typically your finger bones, so those individual phalanges that make up your fingers would fall into that category of being short bones. Then you have what are known as sesamoid bones. And with a sesamoid bone, this is a bone that is actually going to be sunk in connective tissue. So if you were to see it in its true form or placement in the body, the bone itself would actually be hidden and completely sunk into connective tissue. The two best examples we have of sesamoid bones would be the pisiform, which is a small little bone that you have in your wrist, and then your patella is also a sesamoid that is completely covered in connective tissue to help hold it in place and anchor it so that it can do the job that it needs to. Flat bones. Flat bones can be a little misleading because of their name. It sounds like they should be flat on both sides. That's not necessarily the case. In order to be classified as a flat bone, it simply has to be flat or nearly flat on one side. Best example that I can give you here would be the scapula. So we talked about how the scapula lays up against the rib cage, and that side of the scapula is very flat to accommodate that position of being up against those rib bones. The other side of the scapula has a lot of shapes and formations to it so that those muscles can anchor in. So again, if you look at one side of the scapula, it would be very hard to make the case that it's a flat bone. So please keep in mind when we talk about flat bones that it does not indicate that all sides of the bone are flat. Just one side has to have that flat formation. Then the next one we have is the irregular bones. These are the bones that are going to have a lot of odd formations and shapes to them. And if you look at the picture that you have in your packet, it shows the vertebrae as letter D. And that would be an example of an irregular bone. Just a lot of things protruding off of it, a lot of different shapes and formations to it. And that would be your major classification for an irregular bone, just a lot of different formations coming off of it. And then the last one that we have are the Wormian bones. Wormian bones are going to be those found in the skull. And what actually happens is between the plates of your skull, you have zigzag lines. And the reason that you have those zigzag lines is because the bones actually grow faster than what, and they need to be able to protect. And so what happens is when they grow, they'll actually push away from each other. If the bones of the skull were flat when they grew, they would actually separate and they would expose pieces of the brain, just having soft tissue laying over the top of them. Obviously, that's not a good design. So what those bones do is they have a special feature called sutures, zigzag lines, so that when they grow apart, even as those bones start to shift and move away, the teeth of those suture lines will still interlock with each other so that you don't have any spaces where the brain would be exposed. Now, the problem or the issue with the Wormian bones is that they are going to have what appears to be suture lines, even though they're not true sutures. So it gives the appearance that there is a suture or a connection between the two bones, and it is just a formation that you have on the surface of the bone. It's not an actual suture line. Now, the reason that I say the problem with the Wormian bones is because when they were initially discovered, they thought they were bone breaks. And so a lot of people thought that these kids were having skull fractures because they saw these extra lines and formations that were not supposed to be there. They are genetic, so from person to person, these will show up in different places, and some people don't have them at all. And that's why they were mistaken for bone breaks, is because we knew the main suture lines that were supposed to be on the skull, and then all of a sudden you had these additional ones that were showing up. If you skip over to the parts of the long bone, I need to emphasize that this is unique to the long bone only. When we look at your short bones, when we look at flat bones, they will have a different makeup than the long bone. So this is very unique to the design of a long bone. So the first one that we have, you have the epiphysis, and you'll notice that it highlights you have a distal and a proximal epiphysis. Epiphysis is a very fancy way to say end. It's simply indicating that it's the end of the bone. If it's the proximal epiphysis, that is closest to the point of attachment. If it is the distal epiphysis, that is furthest away from the point of attachment. So behind epiphysis, simply write in there that it means the end. And then distal and proximal simply tells you which end of the bone you would be referencing, the closer end or the further away end. Diaphysis. Diaphysis is the middle section of the bone, so this is where the length of the bone would come from. A lot of times people will refer to this as the shaft of the bone. And then below that you have the metaphysis. This is going to be the area between the head of the bone and the diaphysis, so kind of that connection. Some people will reference it as the neck of the bone, but it's just that space in between the diaphysis and the epiphysis. Then we get into the two types of bone structure, and I left a bone out the other day when we met in class so that you guys could actually see this before we had to talk about it. And it showed the difference between compact bone and spongy bone. So it was that cow bone that I left out on the table. And the difference between spongy bone and compact bone, they both are very rigid. And the name can be a little bit misleading. We think of spongy, we think of something that you can kind of squish and manipulate, but both of them are very rigid. It's simply the spacing between the bone cells. In compact bone, there is no space between the bone cells. They are packed together, and you will see no holes in between them. Spongy bone is going to be those places where the bone cells are there, but they are spaced out from each other, and so you can see those actual holes between the bone cells. The difference between the two is that spongy bone is usually going to be very close to your epiphyseal plates or your growth plates. So when these bone cells are initially produced, they are going to be spread out from each other, so they have room to grow and develop, and so that's why you see the spacing between the cells. In areas where you have compact bone and they are packed together, those are your mature bone cells. They've been around for a while, they've had a chance to grow and develop, and that's why they've pushed together and you don't see that spacing any longer between the cells. So when you're looking at spongy bone, you're usually looking at new bone cells. When you're talking about compact bone, then you are looking at places where they have matured to the point, they've grown and developed, and they don't need that spacing in between them any longer. Articular cartilage is a special protective cap that you have on the ends of bones wherever you have a joint. So where two bones meet, you need to have an extra layer of protection so that the bone tissue itself does not rub up against other bone. So these articular cartilage pieces are simply going to cap over the surface of the bone, and they help ease that friction that would normally be there if you had two bones that were able to come in direct contact with each other. The next two that we have is the periosteum and the endosteum. So the periosteum is almost like a saran wrap cover that you have over the surface of the bone. Now, the surface of the bone itself is usually very smooth, and you have a living tissue. When you talk about bones, you have to understand that they are living, and so they need a blood supply. They have to have a nerve supply, and in order to make sure that they have everything that they need, those blood vessels, those nerves have to run very closely to the bones. They run on the outside. Because there's not a whole lot for them to grab onto sometimes because of the slick surface of the bone, that periosteum is a very tight skin covering that will be over the surface of the bone and just hold those blood vessels and hold those nerves in place. If you've ever bruised a bone, what has happened is you have hit that bone with enough impact that you crushed the blood vessels underneath that periosteum layer, and that blood was allowed to leak underneath that periosteum. There's really not any space for that blood to go or to be, and so that's why a bone bruise is usually more painful than just a soft tissue bruise, because it's in a very, very tight space where it's not supposed to be located. They also will take a lot longer to heal than a soft tissue bruise, just because it takes longer to get that blood worked out from underneath that tight skin covering. The endosteum is going to be a skin layer that you also have on the bone, but this is actually going to be on the inside of the bone. And a lot of times we talk about, you'll hear people talk about why birds can fly because their bones are hollow. Well, we have a hollow cavity that runs through our bones as well. It's called the medullary cavity. And the medullary cavity is going to give a place for those blood vessels, those nerves, to be on the inside of the bone structure. The endosteum is going to line the inside of that cavity, and again, kind of help hold and adhere things in place. So periosteum is on the outside of the bone. The endosteum is going to line the inside of that medullary cavity, or that hollow space that you have within the bone structure. For the trabeculae, I'm going to leave that one for right now. And then the last thing that I want to talk about is the red and yellow bone marrow. So within our bones, we have two different types of bone marrow. Red gets its name because it's usually discolored with red blood cells. Yellow marrow is going to get its coloration from the fat cells. So red marrow, a lot of red blood cells, hence the color. Yellow marrow has a lot of fat cells, giving it its distinct color. In a long bone, and again, unique to the long bone, the red marrow is going to be at the ends of the bones, so where the epiphyses are located, that is going to be where you would find the red marrow. The yellow marrow is going to run through the core or through that medullary cavity. So they're in two different locations when you look at the bone structure itself. The next one that I want you guys to take a look at is going to be the compact bone. So this is taking a look at the different, or the structure of the bone itself. Bones are known to be very, very strong, and a large piece of that strength comes from the design of the bone and how the cells are put together. So when you look at the compact bone, the first thing that we have on the list is the osteon. So the osteon is going to be basically a target. If you guys think of what a target looks like, you have a small concentric ring, a center core, and then you have concentric rings around the outside that work their way out. That is exactly the design of an osteon. You have these layers of cell. You have a hollow space in the middle, but then you have these concentric rings that are going to work out from that. And those round rings actually help provide the strength that we associate with our bones. Because if you look at the picture, you have several osteons that are going to be packed next to each other. And if you were to take a toothpick, if you guys had a toothpick available to you and you took that one toothpick and you snapped it, you would be able to snap that toothpick very easily. Wouldn't think twice about it. If you took 100 toothpicks and bundled them together and tried to snap that, now that's a very difficult task to do. So that is the same exact setup that we have with the bone. If you were to take any one of those osteons, just like a single toothpick, you'd be able to snap it. But when you start putting those osteons right next to each other and bundle them together as a single unit, now you have a lot of strength there. So that is the reason that we see those rings in the formation of our bones, is because it provides extra strength so that our bones can take all of the stress that we put on them every single day. The central canal is going to be the space that you have at the very core of that osteon. Again, these bone cells are living. They have to get oxygen. They have to get nutrients. They have to get rid of waste product. That is all going to be provided through our blood vessels. And so the central canal just provides a space for those blood vessels to be able to access all of the cells we have within that bone. Perforating canal, that is going to be those canals that, if you look at the cut or the side view, you can see that you have the central canals which run up and down. And then you have perforating canals which are going to connect them, and they run horizontally. So central canals, blood vessels running up and down. The perforating canal just allows for those blood vessels to connect side to side. Again, all of them running, serving, and feeding those bone cells. Osteocytes, that is your term for a bone cell. If you break that down, osteo always indicates bone, cyte indicates cell. So an osteocyte is a bone cell. Then we get into the lamellae and the lacunae. And so when you are looking at the picture, if you look at the bottom one that's kind of been pulled out, and you can see it a little bit larger, you'll notice that the very last one there is a lacunae. So a lacunae is a space in which that bone cell is going to be housed. Now, one of the features of bone is that it is a matrix design, which means the individual cells do not touch each other. So what happens is you have these little pockets, these lacunae, every so often, and that's where the bone cell is going to be housed. If you are a visual type learner, think of an apartment building. So you have an apartment building, all these people live in the apartment building, but they have their own little unit, their space that they're tucked into. They don't all live in one central area. And so that is the same exact design of our bone cells or our bones. Instead of calling them apartments, when you're talking about a bone, they're referred to as lacunae. A lamellae is just if you take that osteon and if you look at one ring, you could have 5, 6 rings that make up that osteon, but if you pull out just one of those rings all by itself, that's the lamellae. I talked about the bone matrix. The bone matrix is just simply that design that none of the bone cells are going to touch each other directly. And then the last one we have is the caniculi. The caniculi are going to be the canals. That's where the word comes from, canal, and that is connecting those lamellae, or excuse me, the lacunae that you have. So again, these cells have to be able to still get nutrients and everything else, and those caniculi or those canals help get things distributed to those bone cells. The last one that we have are the different types of bone cells, and we already talked about the osteocyte. That's a bone cell, mature bone cell, fully grown and developed. You have an osteoblast. Okay, we see that osteo prefix, and then blast indicates that it is an immature bone cell. So anytime that you see blast associated with it, that is an immature bone cell, still in the developmental process. So that would be part of your spongy bone. Then you have what is known as an osteoclast. An osteoclast is a bone cell that's going to be used when you have damaged bone tissue. So you have a bone cell that is dying or has already died, or you have a bone break where the bone cells need to be dissolved so that new bone cells can come in and heal that break. The osteoclasts are going to contain a digestive enzyme. They will coat the bone cells with the digestive enzyme. They'll be eaten away and make a place for the new bone cell to come in. And then the last one is the osteoprogenitors. Very long name to indicate that is a stem cell. So these are going to be the bone cells that haven't yet got their directions for exactly what type of bone cell they are going to become. They are still in that stem cell stage or formation. So that takes us into the part of the packet that we were able to get to last class. So for this week, I need you to watch the video, take notes, and then make sure that you study for your midterm on the 12th.